So, hi and welcome everyone. I think it's time to start now with this FibRe webinar that FibRe arranging together with us in Treesearch. So we're really happy to have you all here. We are also especially happy to have the speaker, Aleksandar, here, and he will get a proper introduction in just 1 minute by the Center Director, Annette Larsson. So we're going to listen to microscopic insights into the structure, processing property relationships of core shell structures, dialcohol, cellulose nanoparticles. And for you who have been with us for some time, we will have this presentation first, and then we will have the opportunity to ask questions to the speaker. And you who are in Zoom, you can just type a question in the chat. You can raise your hand and we'll let you say your questions and talk directly to Aleksandar. You who are following on YouTube, just type your question in the chat and we will let the speaker get your questions. So with that, maybe I leave the word to you, Annette, to do the real introduction.
Thank you. Thank you, Josephine. Yeah, so today I have the great pleasure to introduce Dr. Aleksandar Mehandzhiyski. You are working at Linköping University as a researcher there. And your background is that you took your PhD in chemical engineering in Trondheim in Norway. And you have been working on multi-scale simulation. And I think that you, during your PhD, was working on crude oil and petroleum-based systems. But since some years back, you are in campus Norrköping. And then you have a little bit changed, but you're still working with multi-scale simulations and MD simulations. But you're now working also on cellulose and other wood polymer-based polymers like lignin. So I really look forward to hear your presentation. So please go ahead.
Yes, hello everybody. Thank you, Annette, for the kind invitation to present in this FibRe webinars. It's a great pleasure to be here. And hello to everyone listening on Zoom or following on YouTube. I hope you all had a nice lunch and are ready to listen about some molecular dynamic simulations of Dialcohol cellulose nanoparticles. So here today I am presenting this work, which has been a really nice collaborations with our colleagues from KTH, MU and PER, and the other from Chalmers. So we have they have been working on this dialcohol cellulose fibers experimentally, of course, and we have joined in to provide some molecular insight into what is happening microscopically in these systems. And so I will start on the other aspects, on the other spectrum of polymers, actually, and I will start my introduction by talking about synthetic polymers and trying to kind of to set up the stage and to give the motivation why we do this work, of course, and in general why this is like a really interesting, I think, really interesting and promising topic. So synthetic polymers, we all know about them. These polymers are really well, characterized, and they have so many different chemistries, and schematically here are some of the most common polymers that we use in our everyday life, and I can hardly imagine our life nowadays without synthetic polymers, and we usually call them plastics. So plastic materials are basically everywhere around us. So they are great materials. They're really cheap and easy to produce in very large quantities. They have really nice and nice properties, like very good mechanical and barrier properties. They are resistant to corrosion and to UV rays. So really they are became an integral part of our everyday life. And of course, last but not least, we can make we can extrude, producing the polymers, extruding polymers into many different shapes that we can imagine, as like with our beloved children toys. Yeah, we can, whatever we can imagine, we can basically produce. And yeah, since synthetic polymers, they have been mass produced from basically the middle of last century, from roughly the 1950s. And as I said, they have really great properties, but this is also their main problem, or not the polymers problem, but our society is one of the main problems of our societies, and this is plastic pollution. And it won't be overstatement if we say that the plastic pollution is one of the most visible and complex environmental issues that we face today. And this is on one hand to these great properties that synthetic polymers and plastics have. So they are very durable, and they have they have a really therefore they have really long lifetimes. So in this schematic here, you can see that more or less, the average lifetime of the mean lifetime of almost the most common polymers are measured in hundreds of years. So more or less all of the polymers that were at one point synthesized in the world, they still exist in one way or another, except the ones that were incinerated. But so there was like a really nice paper from 2017 where this schematic comes from. So this traces the production of polymer, resins, synthetic fibers, and everything from the 1950s to 2015. So we have produced quite a large amount of these polymers, and quite a lot of them are still in use in our everyday life. But unfortunately, most of them have been discarded in the nature. So, and actually, this is most of half of them. And this kind of resulted in, of course, a lot of plastic pollution. And one of the most, famous ones is the Great Pacific Garbage Patch. That's actually there are two. There is Eastern and Western Garbage Patch that basically floats around in the Pacific Ocean. So, and actually, another problem of this is the low recycling rates of polymers, of synthetic polymers, which is about 9%. That's estimated to be around 9%. And in all of these polymers, only below 1% basically are bio-based polymers. And all of these, and the rest is 99.5% they are synthetic polymers. So now we kind of in this slide we talk about plastic products, and next slide. We go one scale basically, well, kind of one scale below, and another part of the problem is microplastics. So microplastics are basically any type of plastics that are less than 5 millimeters. So everything below this dimension is considered as microplastics. And in recent years, I would say that they have started to become kind of more attention to be turned towards them, and to understand how and where basically, and how microplastic are kind of invading almost everywhere, the Earth, invading Earth everywhere. Here in this example, so here we have like a microplastics which have been found in sediments in 4 German rivers. And we see that they're, of course, they're really small, and they're practically everywhere. And we know that microplastic can carry toxic chemicals, so they can bind. There have been quite a lot of studies showing that they can bind toxic metals, and so therefore they serve as a vector for transporting them everywhere practically. And of course, there is a lot of attention towards understanding what are the effects of microplastics on the human body. And well, I think that for some microplastics, we know what are the effects, and they're not very good. But I think that's not all of microplastics. We know what they do to our body. So this is also some research in recent years that is becoming more and more prevalent. So what are they? Yeah, I think I more or less answered this question. The short answer is they're everywhere. In recent years, researchers have found that plastic also complexate with rocks, and they have identified kind of a new rocks called anthropoquinous. I'm not sure that I pronounced it correctly, but so they're kind of a new type of rock that incorporates plastics or other waste, but mainly plastics and rocks. 2021, also they were found in the human placenta. So this means that really the first man-made material that humans are encountering is plastics. And this is actually the last one. The last example is people from Latvia. They try to use microplastics to determine when basically the last Anthropocene epoch started on Earth. Anthropocene is a suggestion that for a new geological era that has been mainly influenced by the human presence, and they were digging on the bottom of lakes, trying and measuring what amount of microplastic there are. So, and however, they were not able to use them to determine where the Anthropocene started, because they were able to find microplastics in sediments even before that were supposed to be before 1950, or where the modern plastic era become into existence. So it means that microplastics are really diffusing also into the human crust more and more deeply. And yeah, although I might sound a bit negative about plastics, I mean, these are the facts, and this is a real problem that we face nowadays. They are great materials, but in general, when we consider their chemical and physical properties, but they're not so great for our environment and potentially for us or other living organisms on Earth. So, of course, these webinars and this FibRe project is devoted to biopolymers. And the logical question is to think, can we replace plastic materials with bio-based ones that can be easily recyclable, or their byproducts at the end would not be so harmful to our environment? And one of the most, the most abundant and one of the most used materials is cellulose. Of course, this is a renewable and natural polymer, and hardly I need to introduce it to this audience here. So if we look a little bit back into the history of polymers, actually, one of the first synthetic plastic material was based on cellulose, and it was called celluloids. It was developed in the middle of 19th century, and it was developed based on nitrocellulose, the reaction of nitrocellulose and camphor. And the original idea why they developed the celluloid was to replace billiard balls because billiard balls at that time they were made of ivory, and of course they wanted to replace this. And they successfully did it. They used celluloid to make billiard balls. However, there was a little bit of a problem, or the problem was that occasionally billiard balls made of celluloid exploded. So that was a that was a really, it should have been a really interesting games of billiard back in the times. And of course, it's a bit tricky when you produce nitrocellulose. You can have quite a lot of you can have problems with explosions and and so on. So it's they kind of I think abandoned it at some point. Another material that we all know is cellophane, which was made from a regenerated cellulose in more or less in the beginning of the last century, which I mean, looking at cellophane, I remember cellophane from when I was a kid. Looking at it, looks like just like a regular plastic material. However, the problem is that it's highly permeable to water vapor, and this is something that we want to prevent in general, although this is quite tricky. So, however, people haven't stopped trying to replace synthetic polymers and plastics with bio-based ones. And one of the examples is dialcohol cellulose fibers. So dialcohol cellulose is basically cellulose fibers treated with peroxide to produce dialdehyde cellulose. So first we have oxidation of the C2, C3 bonds, and consequently we have a reduction of the aldehydes to dialcohol. So basically we open up the glucose ring and we have open kind of cellulose structure. It has been shown that these materials have improved mechanical and gas barrier properties, and more or less they can be easily melt processed with existing technology like extrusion methods, is how I'll show shortly. There have been, I would say, at least 2 or 3 models that try to describe what is the structure of the dialcohol cellulose fibers. Here we have one of these models. They show that, or according to them, this is the peroxide oxidation is highly heterogeneous reaction, and it starts happening at one place at the crystal, and basically progresses when the fiber is oxidized. Second model is the so-called core shell model, where we have unmodified crystalline cellulose, so native cellulose in the middle, and we have a shell of amorphous dialcohol cellulose. And there is also a nice recent paper, a review paper that is kind of reviewing kind of all of these proposed mechanisms, where so here we have the peroxide basically starts its initial attack of the fiber at the amorphous region of cellulose, and after that this is followed by reaction of the surface of the cellulose, then followed again by the kind of penetration of the peroxide and progression of the reaction inside the crystalline core. So, and now I will start with what we have, that was more or less the introduction, and I will start what our experimental collaborators have been doing. They have been melt processing, and of course they have worked quite a lot with dialcohol cellulose. And in this particular work that we did together, they have been melt processing dialcohol cellulose to extrude a material which looks like this. So more or less it's with yellowish kind of plastic looking material. And as we can see in this diagram here, so basically we cannot, or as far as understood, we cannot melt process native cellulose fibers. Therefore, when we convert them into dialcohol cellulose fibers, it is possible to start processing them in normal extruder. So here in this diagram, we show the axial force of the extruder when we melt process these materials at different hydration levels. So this is the fibers were initially conditioned at 30%, for example, in the blue line. And the degree of modification was 41%. And in this experiment, it wasn't able to process the material. But when the material was initially conditioned at higher water content or relative humidity, so therefore it has more water in it, it was able to process and to form basically this filament. And it was easy, of course, to extrude material with a higher degree of modification. But also it was, possible, but a bit harder to extrude the material with 31%. And based on this, we also did some molecular dynamic simulations to see what is happening when we increase the degree of modification, and also when we have more water in the system. And these are the main 2 points what we kind of trying to address with our simulations, which are complementary, of course, to these experiments. So we have done classical molecular dynamic simulations, and kind of this work was, it's roughly divided on in 2 parts. First, the first part that I'm going to talk about is a molecular dynamic simulation of a single fiber. And the second part is about interaction between 2 fibers when we apply a shear force to them, and see how the interactions are. First, so the cellulose, the model that we used is a core shell model. So we have unmodified native cellulose in the middle, and we have a modified dialcohol cellulose chain at the surface of our crystal. We have used this 7x7 chain model, which roughly is 4x3x4 nanometers, and it has a length of 13 nanometers. So of course, we have to be honest and to understand actually that in the experiment our collaborators, they of course extrude fibers, but and they're much longer. But in the simulations, we cannot go to like micrometer scale simulations, at least with these models, and therefore we work with shorter particles, like about 30 nanometers. So more or less, these are you can consider them as cellulose nanoparticles. We have done different degree of modification, and in this case, we have performed our simulations for 25 degrees for 100 nanoseconds. In the other set of simulations, as I said, we had two fibers, and one of them was fixed, and the other one was applied a force to see what are the interactions when we have a different water content, but I'll talk about this a bit later. First, we are starting with the single fiber simulations. I want to introduce basically how more or less the model was constructed. So we have different degree of modification starting from 0 and 100. So at 100, all chains are modified. At 0, we have native cellulose. In the two intermediate cases, we have 25 and 40%. And to build the core shell structure, we have built this model. The gray one represents unmodified cellulose. The orange chains, they have dialcohol moieties in it. And we know, so basically we know that we have chains that are in contact with water, and we have modified this part of the chain. So we have modified basically every second glucose unit that has been in contact with water. And the other part of the chain points towards inside the crystal. So, and we know that, I mean, of course, it's makes sense where the oxidation first to stop to happens at the surface and to progress towards the middle. And therefore, for the 25%, we haven't modified this inner part. For 40%, we applied the same procedure also to the second layer. And yeah, therefore, those two layers are represent the shell structure comprised of dialcohol cellulose. And we have the third type of chain, the blue one, which in this case, it has just those parts of the chain are in contact with water, so presumably they can react also easily, and we have modified yeah, the whole every monomer unit basically. So this is how our models look like. And I should mention that so basically you can create different degree of modification with yeah, in a different way. So you can have a different statistical distribution to your chains and where the oxidized monomer are. So, and yeah, there are many possibilities. Let's look into what we obtained from these simulations. First, we have simulated this, yeah, these fibers for 100 nanoseconds, and we look how their structure look like after 100 nanoseconds. When we increase the degree of modification, we see that this shell of dialcohol cellulose, of course, becomes more and more amorphous, and the crystalline core is preserved more or less. And at 100% degree of modification, the fiber is still kind of holding together, but it's really difficult to recognize the initial structure. Then we have calculated the so-called structure factor, which is more or less corresponds to X-ray diffraction pattern, because we know from the experiments from earlier works that with the increase of degree of modification, the 200 and 110 peak are decreasing. And so we have, due to the oxidation of the cellulose, and more or less we observe the same trends from the simulation. We see the corresponding peaks in native cellulose, and when we increase the degree of modification, these peaks become less and less pronounced. And at 100% degree of modification, we have something, yeah, which looks quite amorphous. If you look then from the other angle, basically, yeah, it's also kind of quite clear that increasing the content of the alcohol cellulose ends up with more and more amorphous region, and basically the fiber also, it looks that it's swelling up and maybe becomes a bit shorter, I guess. At least it's from this looks like from these snapshots. Then when we looked into what is happening with water inside the fiber, so here I have plotted the water distribution around the fiber. So this is for native cellulose. So we see that water is mainly at the surface. And when we increase the degree of modification, water starts to penetrate, and it doesn't have any problem to penetrate through this dialcohol cellulose structure. When we increase it even further, water basically goes all the way insights into the middle of the fiber. Here we have calculated the hydrogen bonds just to try to see how basically the structure behaves when we increase the degree of modification. So for native cellulose, we have about 2 hydrogen bonds per unit. And when we go to, and it's stable throughout the simulation. When we go to, this is the cellulose hydrogen bonds. And when we go to higher degree of modification, they constantly become less and less. When we look into the cellulose and water hydrogen bonds, of course, we see that we have more hydrogen bonds between water and cellulose with increasing degree of modification. And it's steadily increasing with time. Of course, that was only 100 nanosecond simulation, so it's possible that if we leave the 100% modified cellulose, that it will be completely dissolved after a long time. It's kind of is evidence that from here. So that was kind of into just looking and trying to see if this core shell model is stable in is a stable structure, looking into the single fiber level. And now we go into the to look into the fiber interactions. So we have now 2 fibers that are placed next to each other, and they are placed at different separation distance. So we have 2 systems where we have the first system is with distance between the 2 surfaces about 3 angstroms, and this particular case is with 8 angstrom. Okay. So first, let's look like how kind of a typical potential of mean force looks, or the interaction between 2 fibers looks like. This is for native CNC interactions. So this is when we have one cellulose is fixed, and we kind of are varying the distance to the other of the other CNC, and we can see that more or less the strongest interaction is about 3 angstrom, and about 8 angstrom there is a little bit of interaction, but it's considerably smaller. And more or less at 10, 11 angstrom, the 2 cellulose nanocrystals, they don't interact at all. So we have some limit of interaction, which is about 1 nanometer. So let's look what is happening when we apply shearing force to our fibers, or our nanocrystals. Here, these are the 2 systems, or there are much more systems, but kind of we have applying a shearing force in 2 directions. One is in the direction of the axial axis of the cellulose, and the other one is in the transverse direction, so perpendicular to it. In the first case, and both cases, of course, so we have a fixed CNC, and the other CNC is moving. In the top panels here, we see first what is this axial force that we apply, the resulting force, of course, the resulting force of these simulations when the initial separation distance is 3 angstrom. So 3 angstrom more or less is about 1 water layer between them, and 8 angstrom is we have several water layers. So first we see that the interaction, the force is much higher for native cellulose, and we see this stick slip behavior, which corresponds, of course, with this phase about 1 nanometer, which corresponds to the C dimension of the cellulose structure. When we modify cellulose so for the Dialcohol cellulose, we see that the force is much lower at 25 degrees. And when we increase the temperature to 100 degrees, as it is in the experiments, we see that this force becomes even lower for the alcohol cellulose, but also for native cellulose. But still for native cellulose is quite large. When the separation distance is increased to 8 angstrom, basically we don't see any significant interaction between the two fibers, which means that basically they don't feel each other so much, or yeah, just a little bit, and they can just yeah, move freely with respect to each other. Which is kind of also, this is related to the plot that I showed before, where we had this the potential of mean force. Here it's here we have the maximum distance interaction, and about 8 is significantly less. When we look into the transverse direction of shearing, so we see that again, of course, native cellulose has the highest force, and it's decreasing to gradually to 25 and 40, and it's even more decreasing when we increase the temperature to 100. Of course, when we increase the water content or the distance between them, it's practically, we can say it's practically zero. So of course, it was interesting to see that more or less for 25 and 40% here in this case, the shearing force is more or less the same. And here we see some difference with the increase of the concentration. And of course, on the microscopic level, then we have another phenomena which is associated with the entanglement with fibers, which of course it was not captured here in these simulations, but here at least we can see what forces are acting on the microscopic level. Here, this is another way to look basically into these results. This is the tau max, is the maximum force recorded in the simulations. So from the previous graphs for different temperature and the different shearing direction. And both this is the case with the 3 angstrom separation distance. We see clearly that modifying the Dialcohol, the cellulose to Dialcohol cellulose decreases the shearing force quite a lot, which corresponds quite well to, of course, the ability to melt process and to extrude the Dialcohol cellulose fiber in the experiments. And we can say that water is, yeah, the only plasticizer that we need here is water. The second plot shows the interfacial stiffness of that we measured with MD. So this basically shows that this shell region of Dialcohol cellulose is affected quite a lot by temperature. So we have the interfacial stiffness lower significantly when we increase the temperature compared to native cellulose, and that means that these chains are very flexible and they can easily adapt and adjust to the applied forces during the experiment. So, and with that, I think I pretty much covered all the main aspects. So to conclude, we have simulated core shell structure of the alcohol cellulose fibers, or in this case, nanocrystals. And yeah, addition of the water between the fibers, or the water content in this is very crucial in this system, and it lowers quite a lot the shearing force needed for them. And of course, the other two parameters that are important are the degree of modification. With increase of degree of modification, we see that it's more easy to process them. And also the temperature affects quite a lot these properties because of the interfacial stiffness, and that this as a whole, this shell region of the alcohol cellulose becomes more and more flexible and skeptical to shearing. So, and that was pretty much all from me. And yeah, from this presentation, thank you for your attention. And I can try to answer your questions.
Thank you. And I will start to ask a question, and the other ones who are on Zoom or YouTube, you can chat in questions or raise your hand. But I had a question around the hydrogen bonding. You had a slide where you had simulated the hydrogen bonding per unit.
Yes.
The number of hydrogen bonds per unit. I suppose this here, I suppose we can see that the fibrils, when they're more and more substituted, they get fewer and fewer hydrogen bonding in between themselves. Yeah. Is this CNC hydrogen bonds between two nanofibrils, modified nanofibrils?
No,
So
this is within the same fiber.
Is it?
Because it's only once. This is from the single fiber simulation, so this is only one.
Yeah. Okay. Yes. Yeah. Okay.
I have also, yeah, but I didn't include it here, but I have also these plots from for between the two fibers as well. So, and we see also the same trend there. So, but this can be seen from the publication. Yeah.
Okay. So when you add water to this single nanofibril, then you can see that when you have more modifications and you open up more rings, then it interacts, you create more hydrogen bonds with the water. Is this due to that it penetrates into the fibrils?
Yes, and so easily water can penetrate easily inside the fibril, and basically it substitutes the hydrogen bonds with the other chains. That's this is what is happening, and that's why it decreases here and also increases here. It's so, and kind of this can be taken.
Will the total number?
Yes.
Sorry, I interrupt you. So go ahead.
That was kind of this can be taken as indication of kind of also of dissolution of the fibril, basically. Yep.
So will the total number of hydrogen bonds, independent of the degree of substitution, be constant or vary? So if you sum up the CNC hydrogen bonds and the CNC water hydrogen bonds, will it be any differences then?
No, it should be, the total number should be the same, I think, because I mean they is a function of the degree of modification. Yes.
Yeah.
I think
so. The reason why the CNC bonds decreases is that they got another confirmation and therefore don't. Was it water in the first case also, but you just counted the number of CNC bonds in the left image?
Yeah, there is water always in this system. Yeah. So, but yes, the confirmation changes quite a lot.
So I can. Yeah. So the water replaced some of the CNC bonds inside the nanofibril.
Yes, exactly.
Okay, then I got it. Do we have any more questions or raised hands, Josephine, or should I?
I can't see anything. Oh, now we have.
Patrick has one question.
Yeah. Shall we? Patrick, are you okay with
Patrick, do you
asking
want
if
to unmute?
So now you.
Yeah, sure. Hi, thank you for a great presentation. I was wondering, when you designed the cellulose fibers, was the
No, Patrick, we
orientation-
can't hear you any.
I hear.
you can
I
hear
think
me?
it's yes. I think it's Annette has some problems with her connection. So just go on.
Okay. So I was wondering, when you designed the cellulose fibers for the simulations, was the orientation of the cellulose polymer chains considered? In a sense, how the hydroxyl groups are oriented so that do they form cellulose 1 or cellulose 2? And was the alcohol parts initially relaxed or equilibrated, or was there just a C2 C3 bond those just opened?
Yes. Yeah, thank you for this question. So it's this is cellulose 1 beta. So we considered cellulose 1 beta in these simulations, and we didn't consider cellulose 2. So the orientation is they're parallel to each other. And second question. So first, kind of, I have removed the bonds, and then I have just minimized the structure, and then I started the simulation. So I haven't. It's just energy minimization in the beginning. It wasn't like it was kind of a relaxed structure. If it makes sense.
Perfect. Thank you.
This is what you mean, yeah.
We look, Josephine, do you see any questions in the chat or somewhere? Other questions?
No, I can't.
No? Then I can take one when you have the chance to think a little bit to next, and you can take, so the audience can come with questions as well. If we go to this two fibril simulations, when you had two CNCs, you had then you were looking into the force, so the stress curve, and one could see very clear peaks up in the when you have free Ångström's separation there is and then it seems that you have like 1 peak per nanometer more or less. Does that mean that it slips 1 unit?
Yeah.
So it's a stick slip, or how can one explain this?
Yeah, this is exactly the stick slip behavior. When when you apply the force, it slips one unit and exactly goes to about one nanometer down. So this is exactly the difference here. So it's a stick slip behavior. And there was when I was working on this work, actually it came up really nice. Another MD paper on this exactly on this phenomena. It was dealing also with only stick slip behavior, and it was quite nice explained. So I didn't go a lot into details, but this is really what is happening.
But it is much less clear when you move them in this direction, in the Y direction. Do you have any thoughts around that? One can see that they are much more clearer in the A than E case.
Yes, because they
you
go...
slide them instead of when you... So that surface there that you have, it gives less...
I think I didn't hear the whole question.
No, it looks like it froze again.
But so the first, or at least what I was able to hear. Yeah, in this direction, we have this stick slip behavior because we have the C unit of, or when we have the primitive cell structure, when we have the C vector of cellulose, this is exactly the this is exactly when we see this stick-slip behavior only in the axial direction of the crystal, when we have the C vector of the cellulose primitive unit. And this is not so. This is here we look into the probably here we don't have the C vector, so it's not so prominent here. So basically it's missing there.
So we have Per Larsson. You have the ability to talk from the beginning.
Hi, Aleksandar. Good to see you. So when we planned all this, we assumed a core shell model, as you know. And I don't know how much you have followed peridate oxidation papers the last 1 or 2 years, but there is apparently a debate, or there are suggestions that it is not a core shell, but you have a more clustered structure. You had it in the beginning or in the middle, as you introduced dialcohol cellulose, something like this. So if we instead would have simulated something looking like this, do you think there would have been the same effect in terms of lowered shear force needed to slip the particles next to each other?
So if we look into something like this, for example, in this case, or this I think is very similar. I mean,
would it be much more stick slip, or would it be the same, or?
I think it will be much more stick slip because if we assume that we have oxidation happening in the amorphous region primarily, so then we don't oxidize the main part, so we don't oxidize the crystalline part so much, and at the end we have more or less the same CNCs, the same native CNCs. So I mean as you know, our system is much smaller. It's only 30 nanometers, so we are not going to see basically anything. We are just going to see a stick-slip behavior with this.
More basically like the native cellulose.
Yes, exactly. So kind of from this point of view, I think the core shell structure is, or at least I mean it's when you kind of see it in also in the context of the experiment, it kind of makes sense from this point of view. Because when you more and more oxidize the surface, you lower the force needed to shear them. But effectively, if you have a region where you basically have all the oxidation happens at one place, and after that you have a long crystalline region between those two places, therefore the system will be dominated by these regions, by the crystalline regions. And I mean, anyways, the fibers, they have this amorphous region. So if we make it more amorphous with dialcohol cellulose, then our system will be determined by the strongest interactions that are between the crystalline parts, I think.
Okay, all right, thank you.
Thanks.
Thank you. I'm sorry, my net was bad for a while, but I apologize for that. But
I got a really nice reply on your question, so you can rewatch it at any time.
Absolutely, I will watch it on YouTube. With that, we would like to thank you, Aleksandar, for a nice presentation and very nice discussion also with us. And we are saying that welcome you to the next seminar, and that will be the 14th of May, the same time. So we look forward to that. And thank you again for this presentation.
Thank you.
Thank you.
See you.
Bye-bye.
See you.